Swayam Prabha. Digital India. Educated India.
In this lecture, let us begin by recapitulating the reference temperature method, and then we will move on to learn about the governing equations of viscous compressible flow by recapitulating them once again, looking at their flux vector form, and then also going into some more details about calculation of gas mixture pressure, transport properties like molecular viscosity, thermal conductivity, the mixing rules, mass diffusion, the two temperature approach. Many of these concepts are not new to you, but we will discuss them once again in connection with the high to foam solver in the open foam platform. In the previous lecture, we had talked about the reference temperature method, and we said that it is an approximate engineering method for predicting skin friction and heat transfer for both laminar and turbulent hypersonic flow. It is based on the simple idea of utilizing the formulas obtained from incompressible flow theory, and the thermodynamic and transport properties in these incompressible flow formulas are evaluated at some reference temperature indicative of the temperature somewhere within the boundary layer. And since we are dealing with compressible boundary layers, you are aware that such boundary layers often see a very wide variation of temperature. In this fashion, in some sense, the classical incompressible formulas are corrected for their compressibility effects through this reference temperature method. Reference temperature methods also encompass such techniques where reference enthalpy is used, and these enjoy frequent application in engineering oriented hypersonic analysis. The names of the three scientists who proposed it initially: Rubesin, Johnson and Eckert. This is a quick recap, so let us see what we discussed earlier. We considered the incompressible laminar flow over a flat plate, the local skin friction coefficient Cf, the overall skin friction drag coefficient Cf capital, heat transfer coefficient Ch, which are obtained from boundary layer theory of Blasius for incompressible boundary layer flow on a flat plate, are given by these relations. Notice that this is a lower case while this is an upper case. One is for local while the other is for the overall, by accounting for the entire length scale of the body. So, in one case this is Rex, the local Reynolds number, while Rec is the chord based Reynolds number. And then of course, the heat transfer coefficient, which we indicate over here, where the Prandtl number connection also comes in additionally. And the Reynolds and Prandtl numbers are based on the properties at the edge of the boundary layer. That is another important detail that we have to keep in mind, where the subscript E stands for the edge of the boundary layer. In the above expressions, x is the local distance downstream of the leading edge, c is the chord. The compressibility correction in laminar boundary layer over a flat plate is incorporated by evaluating these values for the star conditions. That means, the Rex star or Rec star or PR star, they are to be evaluated at the reference temperature, and thereby you end up getting the Cfs or Ch also corresponding to that temperature. So, that is what is reiterated over here. By definition, these are the coefficients from first principle, and then you are saying that in each one of these expressions, for example, here it is density, you have to apply the particular temperature, and therefore, you end up getting the star quantities. For non-reacting compressible boundary layer, CF and CH depend on the Mach number at the edge of the boundary layer as well as the wall temperature to the free stream temperature ratio. Hence, the temperature within the boundary layer is therefore dependent on both of these parameters. We recall these functional forms from the non-reacting compressible boundary layer theory. Based on that, this reference temperature method has been proposed, more details of which will be found in these two references, that of Frank and Eckert. So, you can explore them at your spare time. And then we remember having done a small problem. Remember that we did the case A, so to say, for compressible boundary layer on a flat plate for conditions at sea level, and then you were also advised to do the case B calculations. And we see very often that the values which fall out of this reference temperature method implementation very closely follow the exact solution of the compressible laminar boundary layer by solving the two ODEs, and the dashed red line that we have over here for the adiabatic wall case is the one for the reference temperature method, which does a slight under prediction. We have seen through the problems that we worked out also, the numbers that came out were slightly under predicting the values from the solution of the ODEs, but nevertheless it is a extremely important and useful engineering tool. So, with that we move on. We look at the Navier-Stokes Fourier equations now over the next few minutes, and this is a rather populated slide, but we need to have a look at each and every corner of this slide, because there is no other way to put in enough details here so that we can see the big picture altogether. We are talking about writing the system of conservation equations in the flux vector form. This is precisely what it means. We will elaborate on this further. So, you have the bold U, the bold F with subscripts I and either INV or VISC. INV, VISC of course means the inviscid and viscous components of flux, and I of course is a particular coordinate direction which is mentioned over here. Correspondingly, the derivative along the respective coordinate direction, and this is again another bold term W, which is basically a source vector. When we are talking about vector, it has multiple components, and the multiple components essentially address the multiple conservation equations. If you were to expand the U vector, it is basically a column vector, but we have written it in a horizontal manner in a row form with a transpose here, which basically means that it is a column vector, contains all the components of the U vector starting from rho, rho S. Rho S is nothing but the partial density of species S. The subscript S will be used for addressing the different species which exist within the reacting gas mixture. Then rho U, rho V, rho W, and E, V, M and E. So, when it comes to defining S, S belongs to N S, which is the number of molecules or rather number of species. So, this is a small mistake here. So, please correct it to species, and N M is the number of molecules that we are talking about. So, we will discuss further on the idea of EVE or E, but briefly speaking, it is EVE stands for vibroelectronic energy of molecules. The subscript M part stands for molecules, which we said is comprised of N M number of species, and the capital E stands for the total energy. Further, In the next equation, you will see the presence of the Kronecker delta, which you have seen earlier also. So, if you recall that it takes up a value of 1 when I is equal to j, that means both the indices are equal, and will take up a value of 0 when the indices are different. The subscript Tr stands for translational and rotational energy mode. The subscript Ve stands for vibrational and electronic energy mode. So, there is a lot of nomenclature which you have to keep track of over here, but it is not very difficult, you will get used to it. Now, if you look at the F vector, it has been split into inviscid and viscous parts, and if you go term by term, you will be able to understand that it actually contains different components like the way the u vector contained. So, let us see, the first component is rho ui, the second component is rho s ui, and so on. So, we will see them once again in a column form in a subsequent slide, where it will be easier for you to see each and every term put together. Remember that each one of these vectors are indicated with a T superscript, which means it is basically a transpose operating on the row form that we have written here, which means they are all column vectors. We have not written the form of the source vector here in this slide, we will see later. There are more relations which will need to be implemented into the flux vector form of the equations in order to solve them. One of them is the pressure of the gas mixture, which is actually going to come from all the constituent partial pressures. We will discuss more of it later. Viscous stresses, of course, we have described and discussed at length in earlier lectures. So, we will not discuss it anymore. Heat flux, which has to do with the different components indicated by I, along which the Fourier's law is expressed. Here it is talking about the translational mode, and when it comes to the vibrational and electronic mode, you see a summation coming from different species. More details of this formulation can be found in the following two references, which have been mentioned for your later study. We repeat once again that U is a conservative flux vector, and the flux is decomposed into two parts, inviscid and viscous, as far as the F vector is concerned, and the source terms are on the right hand side, which we see with the W dot vector. In order to get the closed form solution of this equation or system of equations, better to say system of equations, some extra equations need to be solved simultaneously. Now comes the column vector form, as I was saying in the earlier slide. So, conserved variables flux vector is U, the viscous flux vector is this, the inviscid flux vector F is this, and finally, the source flux vector is this. So, you see all of them together. Now, you have hopefully a better view of all the components, and I hope you can also identify them. For example, these terms are coming from pressure gradient, if you can identify them. These are the advection terms. Similarly, these are the viscous terms. You should be able to also identify terms which are associated with mass diffusion, for example, or thermal conductivity. So, those are already taught, and you have to recapitulate all the equations that you have learnt about earlier, so that you are able to map them all. We learn more about the terms that we see in the source vector in a later slide. Now, let us look at the two bullet points here. The concept of flux vector splitting can be applied to split the fluxes based on eigenvalues, and then apply suitable discretization to approximate the split flux terms for computing the flow. So, when we say flux vector, we often apply the technique of splitting the flux based on eigenvalues, that is obtained through a certain procedure, and then based on the signs of the eigenvalues, they would all be real eigenvalues if this is a strictly hyperbolic system. Then we split them into their positive and negative values and order them in terms of increasing magnitude, and then we deal with them in terms of the numerical discretization. So, that is basically the idea. Of course, different types of flows can be solved by using these equations based on the different geometries that you choose and the flow conditions that you impose. You can consider viscous, inviscid flows, equilibrium, non-equilibrium flows, reacting, non-reacting flows. All kinds of possibilities are manageable within this framework. You certainly need to look at one important assumption that you should be able to fulfill, that of continuum. This is an important assumption which should be fulfilled for these equations to work. Now, as I mentioned earlier, this equation for P is based on the concept of partial pressures, and we apply the calculations of Dalton's law in order to get information from this equation. This is of course the viscous stress calculation. This equation deals with translational and rotational heat flux calculations, and then the final one here is vibrational heat flux calculation, and the source term we already saw, and some more detailed weighting in the subsequent slides. In the meantime, let us have a quick look at the nomenclatures once again, just to recapitulate them. Some of them appear in the form of subscripts, while others are in the form of symbols which occur as such in the different equations. So, when we say subscript m, it refers to a molecule, subscript Tr, then its translational and rotational energy mode, Ve is for vibrational and electronic energy mode, E alone is electron energy mode, number of molecules Nm, similarly number of species is Ns, Boltzmann constant is K with a subscript B, species as such is indicated with subscript S. The different coordinate directions are indicated with the subscript I. Mass diffusion vector by the bold J, Kronecker delta, delta Ij, density of the different species which form the mixture by rho S. The mass diffusion vector of S species and I direction would be given by a nomenclature like this, and mass diffusion vector due to molecular diffusion of S species and I direction would be given by this, where M stands for the molecular part. The heat flux associated with translational and rotational mode of energy and I direction, that means the component, will be indicated by this. So, one part gives you the information about translational and rotational, the other gives the I direction. Similarly, the heat flux associated with vibrational and electronic mode of energy and I direction will be given by Q, V, E, comma I. So, there are a lot of nomenclatures involved here, most of them are mentioned here for quick reference. Now, going to some more detailing. The partial pressure calculation by Dalton's law would come up like this, and remember that here we are summing over different species, however, not the electronic energy mode. We have a separate term doing that over here, and the term that you have over here is the capital T with Tr in the subscript, which represents the translational and rotational part, not the electronic energy part. So, the electronic energy part is segregated out, and it is basically involving the electronic bond energy. So, here this part of course would have to do with the ionization part of the reactions. So, you have to take care of that distinction, that it is not changeover of an electron from one particular energy level to another within an atom or molecule. It's a question of breaking the chemical bonds and therefore forming free electrons and the ions. Source terms which we have been talking about, let us elaborate them a little bit more. So, this W is of course the source term column vector. Since chemical reactions are occurring, the source terms would be non-zero. Therefore, the source term basically represents effects from chemical reactions, and let us see what this term stands for. It is the net mass production for each species in the mixture. You have zeros in between that essentially represent body forces, but we are ignoring them, and then the final one W dot V m, it is the net mass production due to molecular diffusion affected by vibrational mode of energy. So, the vibrational and often vibrational and electronic is clubbed together. It references the molecules, and therefore, it is applicable only for the molecular species in the mixture. The transport properties calculation, let us see how we do it. So, for mu s, where S of course stands for the species, we have omega s in the exponent. It is the temperature coefficient of viscosity of species S, and it should not be confused with the mass production term W s dot appearing in the source term column vector. So, just going back once, what we mean to say is that you should be careful that this omega s dot term is not confused with the omega s that is in the exponent here. Now, in this mu s equation, you have a mu ref term for each species, and if you expand that, it looks like this. There are several terms in the expression, and every time remember that the subscript s stands for species wherever it occurs. The small m s which appears here is mass of single particle of the relevant species, whether it is an atom or molecule. Then d ref is reference diameter, then Kb of course is Boltzmann constant, d ref comes up here, and then T ref which comes up here as well as over here. It is actually some reference temperature, standard values are available from the tables. So, this is how you calculate the mu ref value, and you plug it in here in order to get the mu for a particular species. Going to transport properties calculation, where we look at thermal conductivity calculation. The K for the translational rotational part is calculated using this formula, where you have CVTS, CVRS figuring, where both of them are specific heats at constant volume for either translational or rotational mode of energy. So, you sum them together to get that for translational and rotational, and of course, mu s is plugged in for each species based on the calculation we showed in the previous slide. Then going to the vibrational and electronic, you have the CV VES, which is specific heat at constant volume for vibrational and electronic energy modes, and based on that you calculate the thermal conductivities. One point that we need to remember over here is that we also need to have mixing rules. So, we have to invoke some rule. We make use of the Wilks mixing rule, and there we see that the mu s that you have already calculated earlier is multiplied with the molar fraction of the species S and divided by a blending factor corresponding to those species, and it applies to all the ns number of species. The summation is done over all the species, and then you have the expression for phi s, which is showing up in the denominator of the summation. So, in the phi s expression again you have the molar fraction coming in here, and then a rather complex expression here involving the molecular weights of the different species, and you sum it over all the n species, where only thing that you have to remember is that R should not be equal to S. So, you take all the remaining species other than that particular one when you do the calculation here. A similar formula can be obtained for thermal diffusivity, for example. So, this is the way we calculate the mixing rule, and then we look at mass diffusion. In the mass diffusion, we have an equation looking like this, and the terms work out like this over here. The JSI are the diffusion flux of species S along direction I, which are governed by modified forms of Fick's law, which we have learnt earlier, which ensures that the sum of diffusion mass fluxes is 0, which is very important. And then the different terms which figure, the Ys is mass fraction, ds is effective diffusion coefficient of species S in the mixture. Then Le, which figures in this equation, is Lewis number, and you remember having learnt about it in an earlier lecture, lecture 49, where we had written down the expression for binary gas mixture, and you remember it gives us the ratio of energy transport caused by diffusion relative to thermal conduction. Again, remember that wherever the subscript Tr comes up, it is translational and rotational, and Cp_Tr of course is mixture heat capacity at constant pressure. In the above Lewis number model, that means a model based on Lewis number, the effective diffusion coefficient is identical for all neutral particles. So, we have a common formula for all neutral particles, and the effective diffusion coefficient for charged particles is double that of neutral particles due to what is called as ambipolar diffusion. The ions and electrons move together as a single gas, where you have a mixture of them. There is diffusion of positive and negative species with opposite electrical charge due to their interaction in the ionized gas, and therefore, you have twice d for charged particles. That is basically the rule that we follow for such ambipolar diffusion. Going to the implementation of the two temperature formulation, let us see how we do it. We begin with writing an expression for the total energy. Recall that the expression that was used was capital E in terms of the different energy pools existing in the flow. So, let us see what they are. If you look at the right hand side of this equation, it comprises of kinetic, translational, rotational, vibrational, electronic and electron. Further, chemical energies. So, when we say electron energy, it is associated with breaking the chemical bonds and leading to ionization, which we have mentioned earlier also, and that is what stands out over here, while the electronic part is with a subscript EL. Keeping that in mind, let us look at the remaining points that we have over here. The above procedure has the motivation of isolation of different energy pools, each one of them being described by a specific temperature and exchanging energy with other pools. So, this is basically the motivation behind expressing the total energy in a form like this. If you look at the first term, which actually carries the kinetic part, it indicates Ui square, where of course Ui is the spatial component of velocity vector, and then if you look at the last term, Hs naught, its standard enthalpy of formation of species S. We need to recall about 0 point energy, which we have learnt earlier. So, these are easy to grasp concepts at this point of time, where you already have a good amount of maturity in this domain. Now, let us see how we mature it to a two temperature formulation following the proposal of Park. So, during the process of relaxation towards thermal equilibrium in a non-equilibrium flow, what happens is the translational and rotational energy modes achieve equilibrium within a small number of particle collisions. So, in a two temperature formulation, the translational and rotational temperature are considered to be in equilibrium at any point of time, and they are thus equated to the transrotational temperature T with a subscript Tr, while the electron and electronic energy modes are assumed to be in equilibrium with the vibrational energy modes. Therefore, all three temperatures which we see here, electron, electronic, vibrational. So, these three energy modes are assigned a vibrational, electron, electronic temperature combined, which is Tv subscript m, and remember that that is applicable only for molecules, and thereby you have the segregation into the two temperature model. Remember that the translational part sums up the contributions coming from translational and rotational. The vibrational, electronic or electron sums up the contributions, or rather vibrational and electronic sums up into EVE and so on. Finally, the overall temperature formulation, let us see what it is about. It contains terms like XS, which is molar fraction of the different species. Remember that it is actually a sum divided by another sum. The zeta terms indicate number of degrees of freedom of a specific energy mode. Let us see what the degrees of freedom for the different energy modes turn out to be. Translational and rotational energy modes are assumed to be fully excited, therefore 3 degrees of freedom, therefore zeta Ts is 3. 2 degrees of freedom for the rotational energy mode, zeta Rs is equal to 2. Rotational energy about nuclear axis between two atoms in a diatomic molecule is negligible, and the remaining zeta terms, they need separate equations, which we are not probing here for the sake of brevity. The overall temperature which comes out as a consequence is the actual temperature that the gas particles feel as they move through the flow. Consequently, those particles that impinge on the vehicle surface immersed in such a flow would influence the temperature that is felt on the vehicle surface. This temperature carries an overall effect of the different molecular temperatures and their respective degrees of freedom. So, this is the significance of the overall temperature. Let us conclude by saying that in this lecture, initially we recapitulated the reference temperature method. We then revisited the governing equations of viscous compressible flow and expressed them in their flux vector form. Calculation of gas mixture pressure from partial pressures, transport property calculations of molecular viscosity, thermal conductivity, followed by mixing rules, then mass diffusion and the two temperature approach. All these concepts which we have learnt earlier too were discussed in detail, especially from the point of view of implementation in an open source CFD solver, namely the Hy2Foam. So, this helped us go into further details of all these aspects of numerical solution from the context of an open source solver. Thank you.